Visual, black screen. Then, slowly, a single point of light appears. A satellite catching sunlight against the darkness of space. Somewhere above your head right now, 250 miles up, moving at 17,000 miles an hour, a machine is thinking. It has no walls, no roof, no air conditioning humming in the background, no power cord running to a wall socket. And yet, inside it, billions of calculations are happening every second. The same kind of calculations that power your search engine, your weather forecast, your voice assistant, maybe even the video you're watching right now. Visual. Cut to Earth from orbit, the thin blue line of atmosphere hugging the planet. For 70 years, we've believed a data center needs three things to exist: a building to protect it, a power plant to feed it, and an ocean of cold air or water to keep it from melting itself alive. What if all three of those assumptions are wrong? What if the next great leap in computing isn't a bigger building, but no building at all? Visual, aerial drone shot of a massive data center complex, rows of gray warehouses stretching to the horizon, cooling towers venting steam. To understand why anyone would try something this radical, you first have to understand the crisis hiding behind every device you own. Every time you ask an AI a question, stream a movie, or send an email, that request doesn't just vanish into the cloud. It travels, often hundreds of miles, to a physical building packed with racks of humming servers, real machines, real heat, real electricity. And right now, those buildings are running out of room to grow. Visual chart animation, U.S. electricity demand curve spiking upward. In the United States alone, data centers may require more than 100 gigawatts of power by 2035, and global AI-related demand could eventually approach 1 terawatt. That's not a typo. That's roughly the electricity output of dozens of nuclear power plants, just to keep servers running. Visual, diesel generators, transmission towers, a grid connection denied permit document. Data center development is running up against 7-year power queues, water scarcity, and regulatory resistance. Entire towns have pushed back against new data centers moving in, worried about strained power grids and drained water tables. Because here's the part most people don't know. Keeping a data center cool is almost as expensive as running it in the first place. Visual, thermal camera footage, server racks glowing orange with heat. Roughly 58% of the electricity a data center consumes isn't used for computing at all. It's used for cooling, fans, chilled water, massive air conditioning units the size of school buses. All of it exists for one reason. Computer chips generate ferocious heat, and if that heat isn't removed, the chips fry themselves in minutes. So the question engineers have quietly been asking for the last few years is almost absurd on its face. What if we stop trying to cool data centers on Earth and put them somewhere there's no air to fight against in the first place? Visual, slow zoom out from Earth into open space. That somewhere is orbit, and the story of how we got there starts with a much older idea than you'd expect. Visual, grainy 1970s NASA archival footage. Solar panel diagrams, chalkboard sketches. Believe it or not, humans have been dreaming about putting technology in orbit to escape Earth's limits for over 50 years. In the 1970s, physicist Peter Glaser proposed something wild: giant solar panels in space, beaming energy back down to Earth using microwaves. The idea was mocked as science fiction. The technology to build it simply didn't exist. The visual 1990s satellite launches, early internet server rooms with beige towers. Fast forward to the birth of the internet. As data centers multiplied across the planet in the 1990s and 2000s, engineers already knew cooling was their biggest enemy. Companies started chasing cold climates, building server farms in Iceland, in northern Sweden, anywhere the outside air itself could help do the cooling for free. Visual, Google's Finland data center, ocean water intake pipes. Google even built a data center inside a former coal power plant, and companies started running seawater through pipes just to steal a few degrees of natural cold. But cold air on Earth has a limit, and demand for computing power was about to explode past anything the planet's climate could handle. Visual, 2020's AI boom montage. Chatbots, chip factories, GPU racks. Then came the AI boom. Suddenly, the world didn't just need data centers. It needed data centers that could think. Training a single large AI model could burn through more electricity than a small city uses in a year. Engineers went back to an old, half-forgotten idea. If Earth can't give us enough cheap power or cold air anymore, what does? Visual, sun rising over Earth's horizon, seen from orbit. The sun, constantly, without clouds, without nighttime, without a single power line. That single realization would quietly restart a 50-year-old dream. And this time, the technology had finally caught up. Visual, FCC filing documents, satellite constellation animations, forming a mesh around Earth. Here's where the story stops being theoretical. Because right now in 2026, this race is already underway. SpaceX has filed with the FCC for 1 million solar-powered orbital data center satellites, aiming for 100 gigawatts of AI computing capacity per year. 1 million satellites. Let that number sit for a second. That's more objects than every satellite ever launched in human history, combined. Visual. StarCloud logo. Satellite render with deployed solar wings. The startup StarCloud has applied for a constellation of up to 88,000 satellites. Blue Origin has filed to deploy 51,600 satellites for data center operations. And it isn't just American companies. Visual. World map, lighting up with orbital launch sites. US, China, Europe. China's Ataspace is pursuing similar concepts, and Google's Project Suncatcher plans constellations of AI chip satellites with launches proposed as early as 2027. Even the European Union is studying its own version under a project called Ascend. In just 3 years, this went from a napkin sketch to a global race between the biggest technology companies and governments on Earth. But here's the twist that makes this so dramatic. Almost every one of these companies is racing toward the same brutal, unsolved problem. Visual, a satellite in orbit, close-up on server hardware inside, heat, shimmer visualized in red. Because being in space doesn't magically make heat disappear. In fact, it makes the problem harder in one specific way. On Earth, we cool data centers with airflow, liquid cooling, and fans. In the vacuum of space, none of that works. There's no air to blow, no water to flow. As one engineer put it bluntly, there's nothing that can take heat away. So how do you cool a computer in a place with no air at all? Visual. Slow motion shot of a satellite's radiator panel unfolding like a metallic flower. The answer sounds almost too simple to be true. You don't cool the computer with something. You cool it by pointing it at something colder than anything on Earth could ever be. Deep space itself. Visual, animated diagram. Heat radiating off a flat panel into black starfield. The extremely low background temperature of deep space allows heat from onboard computers to radiate directly outward through passive radiative heat transfer. No water, no fans, no moving parts required. Every object in the universe naturally sheds heat as invisible infrared light. On Earth, that process is slow and weak because our atmosphere traps heat around us like a blanket. But in the vacuum of space, with nothing in the way, that same radiation can escape freely into a background that sits at nearly absolute zero. Visual split screen. The data center's noisy AC units versus silent satellite radiator glowing faint red under infrared imaging. It's not cooling in the way we've always understood it. There's no chilled water, no condensation, no electricity spent moving air, just flat panels angled outward, quietly bleeding heat into the coldest sink imaginable, the universe itself. And solving the power problem turned out to be almost poetic in comparison. Visual. Solar panels catching direct, unfiltered sunlight. No clouds, no atmosphere distortion. Some low Earth orbits, called sun-synchronous orbits, can give satellites near-continuous solar energy. Sunlight that never dims, never sets, and never has to fight through clouds or atmosphere to reach the panel. Solar-powered orbital data centers can harness roughly 25% more useful solar radiation than ground panels, while producing continuous electricity if kept in constant view of the sun. No power lines, no fuel deliveries, no permit fights with local towns. Just sunlight, direct and uninterrupted, feeding the machine every second it's in view of the sun. Visual. Wide shot, a full orbital data center satellite, solar wings extended one side, radiator panels extended the other, servers glowing faintly in the middle. No building, no grid, no air conditioning. For the first time in the history of computing, engineers had designed a machine that could think without ever touching the ground. But a breakthrough on paper is one thing. Making it survive up there is another story entirely. Visual. Rocket launch, payload fairing separating to reveal a satellite. This isn't a concept trapped in a lab anymore. Pieces of it are already flying. A startup called Lumen has already flown a single NVIDIA H100 GPU on a satellite, proving, in a small but real way, that today's most powerful AI chips can survive launch, radiation, and operation in orbit. Visual. Diagram of a satellite constellation communicating via laser links, beams connecting node to node. And these satellites don't just compute in isolation. Laser links between spacecraft could reduce dependence on much of the physical internet infrastructure required on the ground, letting data hop machine to machine at the speed of light, without a single fiber optic cable buried underground. Visual, timeline graphic, 2026 present day, marching forward to 2027, 2028, 2030. Google's Project Suncatcher has a demonstration mission planned for 2027, the first real test of whether AI chips can run meaningful workloads in orbit, not just survive the trip. Visual, a satellite constellation forming a glowing mesh around the planet, subtly pulsing like a network diagram. Imagine for a moment what this actually unlocks. A wildfire detection system that processes satellite imagery in orbit, sending down only the answer. Fire detected here, instead of terabytes of raw video. A translation AI serving disaster relief teams in a region where the ground infrastructure has just been destroyed. A weather model that updates constantly, fed directly by the same satellites doing the sensing. None of this replaces your neighborhood data center tomorrow. But it doesn't have to. It only has to prove the model works, because once it does, the economics of computing change forever. Visual, stock ticker graphics, tech company logos, Google, SpaceX, Blue Origin, NVIDIA. The money chasing this idea is staggering, and it tells you how seriously the industry is taking it. Analysts expect the orbital data center market to rise from around $1.77 billion in 2029 to nearly $39.1 billion by 2035, a compound annual growth rate of about 67%. That's not gradual growth. That's an industry preparing to explode. Visual, boardroom silhouettes contrasted with a rocket launch pad at dawn. Even as tech companies are projected to spend more than $5 trillion globally on Earth-based data centers by the end of the decade, some of the very same companies are quietly hedging their bets on space, a signal that even the people building today's giant server farms aren't sure the ground can keep up with tomorrow's demand. Visual, a small town, protest signs about water usage and power lines outside a data center construction site. And there's a second, quieter kind of impact, one that has nothing to do with computing speed at all. Local officials have begun pushing back against new server farms that swallow land, strain power grids, and consume enormous amounts of cooling water. Some tech executives now see orbit as a way to escape those permitting fights entirely. But before this sounds like a fairy tale ending, the skeptics deserve their say, because their warnings are just as important to this story. Visual, a crowded orbital simulation. Thousands of satellite dots swarming around Earth. A significant increase in the number of satellites in orbit could be difficult to manage, and could raise the risk of collisions. Cooling, maintenance, radiation exposure, and orbital debris remain major hurdles that no company has fully solved. One energy researcher put it plainly: while the known cost of scaling data centers on Earth is already high, the unknown cost of sending them into space at massive scale may be even higher. Visual, a satellite dish, then a night sky filled with faint moving points of light. Astronomers have raised their own concern that a sky filled with thousands of bright, reflective data center satellites could interfere with the very telescopes we use to study the universe those satellites are floating in. This isn't a guaranteed victory. It's a genuine race against real physics, real economics, and real consequences. A visual, a slow, sweeping shot from the surface of Earth, tilting upward through clouds into black space past a glowing satellite constellation. So where does this leave us? Somewhere between two extremes. On one side, full-scale sky factories, hundreds of thousands of satellites forming a computing shell around our planet, running the world's AI on pure sunlight and radiating their heat silently into the dark. On the other, a costly, complicated dream that never scales past a handful of demonstration missions. The truth, almost certainly, sits somewhere in between, and that's actually the more exciting outcome. Visual, a hybrid Earth and orbit network diagram, ground data centers and orbital satellites working together, glowing connections between them. Picture a future not where space replaces Earth's data centers, but where it relieves them, where the most power-hungry, heat-generating AI workloads quietly move off-planet, freeing up rivers, power grids, and land for everything else. A future where a wildfire is spotted and analyzed before the smoke is even visible from the ground. Where a satellite doesn't just take a photo of a hurricane, it thinks about that photo instantly from orbit. Visual, time-lapse of a satellite constellation growing denser year by year, subtly overlaid with a ticking clock. By 2027, we'll know if AI chips can actually work, not just survive in orbit. By 2030, we'll know if the economics make sense at scale. And by 2035, if the optimists are right, the sky above you may quietly be doing some of the thinking your phone takes credit for.